I started 2 editions prior, so 4 years ago here in Complas on data-driven methods, or our own particular brand thereof. I think that this is really an area that is a growth area in science and also, of course, in computational mechanics. So, I mean, it's here upon us, and I think it behooves the community to figure out what's in it for us. And the reason why I think it's a growth area is not just a flash in the pan like so many other subjects, is that there's been a tremendous revolution in experimental science, definitely since I was a graduate student at Berkeley. In those days, we had MTS machines, and if you were lucky, you would have 1 data point or 2, and you would put a straight line through the points, and that would be your material modeling, okay? So now we sit on really mountains of data that are obtained through a number of methods, such as, for instance, digital image correlation, which I'll refer to later on, okay? So these methods give you not just point data, but really full field data that contains a lot of information about the material. So we have transitioned from a data-starved world, okay, to a data-rich world. And the question is what to do with all the data, okay? And of course, there are many answers, and I'm going to tell you exactly what our particular answer is. And so if you look at the role of material modeling in traditional computational mechanics and computational science, so nowadays, as I said, you would have full field microscopy providing mountains of data, and then when you do material modeling, you reduce all that information to just a few parameters. Parameters that depend on the model that you assume. So you make assumptions about the functional form of your model. That model is parameterized by a few parameters, and then you identify them based on the data, and you throw away the rest of the experimental data. So it's extremely wasteful. And then based on that material model and those few parameters, you engage in high-performance computing, and you generate, again, lots and lots of manufactured data. So somehow there's a bottleneck here. There's a broken link between modern microscopy and modern prediction. And the way we see, or one of the roles that we see of data-driven mechanics is to actually forge a more perfect union, okay, between microscopy and prediction, so observation and prediction. And the way we propose to do that is to actually set and then solve boundary value problems. So in a way, we formulate all the boundary value problems of mechanics directly from the data, okay, and completely bypass the modeling step. Okay, and so that way we eliminate the modeling bottleneck, and we establish a direct connection between data and prediction. Obviously, that's a rather extreme paradigm, okay, but if we thought it was worth exploring, there are many other ways of doing things. Okay, so of course, you're not going to throw away your models, and perhaps there are hybrid approaches also where you do bits of modeling, bits of model-free data-driven mechanics. So there is all sorts of possibilities. We decided to explore the new one, okay, which is model-free data-driven mechanics, just to see what we could get out of it. Okay, so this is the way I see now this approach. Okay, so it really, the entire story has several parts. Of course, there is solvers. Okay, so, oops. Okay, so you have to be able to take the data and somehow process it into predictions, so that you require data-driven solvers. But then there is also a big question of where does the data come from, okay? And how do you generate data in a way which is consistent with these data-driven methods? And also, I think there is a very interesting aspect, especially for industry, of how to manage data repositories, okay, material data repositories, okay? I think another reason why this area is probably a growth area is because in my experience, industry really hates modelers, okay? So industry generates a lot of data from testing. They spend millions and millions and millions of dollars or euros doing testing. Then they have a lot of data. In order to use those data for prediction and design, they have to bring in modelers that proceed to defile the data, okay, and reduce it to models that are nowhere near as good as the data itself. So I think this has been always a bottleneck in industry to go from the data they have and they acquire at great cost to the designs and predictions they want to make. Okay, so that's, I think, another big driver. Okay, so today I'll say a little bit about solvers, and then we spend a lot of time thinking about data mining and how to do it in a self-consistent way, and a couple of words about the data repository business, okay? So I start with solvers, and this is perhaps the part of the story that is better developed. So I'll just summarize where we stand at this point. And I always start with a simple example that I think tells most of the story. Okay, so perhaps 90% of the story. So very often in science and in computational science in particular, the whole key is to find the key example, okay, that tells you exactly how things work. So I think this is one of the key examples. So imagine that you have a bar, and you actuate the bar with a loading device that represented by the spring. The spring will have some stiffness, and you have a control, which is the displacement you apply to the spring. So this is going to be in a state of uniform deformation, so there is only one strain, one stress, assuming the material is stable, okay? And so the phase space where data-driven analysis takes place is the space of strains and stresses. That's what we call phase space. These are work conjugate variables, and together they define a space which is the phase space of the material, okay? So now compatibility and equilibrium establish constraints that the fields need to satisfy to be admissible, okay? So of course the solutions have to be compatible, have to be in equilibrium. For this simple example, you write down, okay, the back of an envelope, the compatibility condition, the equilibrium condition, and you find that those together introduce a linear constraint between strains and stresses that you can represent as a linear, as a line in phase space. So this would be a constraint subspace, which is the subspace of all the states that are admissible, that satisfy the conservation laws, whatever those might be. In the case of mechanics, of course, would be compatibility and equilibrium. So then, okay, so there's a constraint set, and then you assume that you have characterized the material, and all the possible states of the material define another subspace, a phase space, which is the data set, and of course the solution is at the intersection. And the solution will exist, assuming that there is some transversality condition is satisfied between the data set and the constraint set. Okay? So now imagine that contrary to that picture, okay, so we only know the material behavior through a data set. Data set which is a point set. Each point could be an experiment, a lower scale calculation as we'll see, and so on. So this is all you know about the material behavior. Of course, the traditional paradigm would be to fit it somehow. Nowadays you use machine learning to fit it, still fitting, okay? Fitting by any other name is still fitting, okay? So in general, there won't be any point in the material set that is admissible. So the intersection between E and D is generally empty. So what to do? You have to generalize the notion of solution. So you take as the best possible solution the point in phase space. This would be Z would be strain and a stress field that is admissible, and it is as close as possible to the material data set. So in this case, it would be this point there. Okay, so this point there, and the nearest point on E would define the data-driven solution. So it's a redefinition what it is to solve the problem based directly on a data set. Okay. Maybe this would be a good moment to turn off your cell phones. Thank you. Okay, so these are the elements of model-free data-driven computing. So you have a data set in phase space, a constraint set, which would be the admissible points in phase space that satisfy all the conservation laws. Conservation laws, by definition, are material independent. Okay, so they're universal, therefore. And then this would be the solution, the data-driven solution would be the closest point on the data set on the constraint set, or the point of the constraint set that is closest to the material data set. Okay, so that's what is stated there. And then there are a number of differences with traditional data methods. So here, of course, we emphasize fundamental data in phase space, so stress and strain in the case of mechanics, okay, and the fact that the data is used directly and processed in the calculations. So therefore, there is no material modeling and no loss of information with respect to the data set. Okay, so here's another example taken from structural mechanics. Okay, we love structural mechanics. So this is the case of a truss. Okay, a truss is particularly convenient because the phase space is two-dimensional. It's just an axial stress and an axial strain. And say that the behavior of each individual bar is defined by a point set. And that's all you know about the material, okay? Well, so again, in this case, the degrees of freedom would be the nodal displacements. Okay, so I'm going through this exercise to exhibit the structure of the so-called DD solvers. Okay, they have a very particular structure, which is worth pointing in detail. Okay, so here we have the nodal displacements will be the degrees of freedom. Phase space will be the collection of bar strains and bar stresses. E here labels the members in the structure. M would be therefore the number of members. You metrize that space with some norm. C is just, it's not a material parameter, it's just a metric tensor, okay, that defines the distance in phase space. The constraint set, of course, is the usual set of strains that derive from a displacement field through the B matrix. Okay, we all know what the B matrix is. And then B transpose would be the discrete divergence operator. So the constraint on stress is the equilibrium condition that B transpose times stress be equal to the applied loads. So that would define the constraint set. And now the data-driven problem is a distance minimization. So you want to find the admissible set of strains satisfying compatibility and stresses satisfying equilibrium that is closest to some material state, epsilon star and sigma star, that has been identified as being part of the material data set. Okay? So again, the interesting point is that, of course, I mean, this is just a discrete minimization, so it entails searching in some intelligent way through the material data set, okay? But the other interesting point is that if you compute the Euler-Lagrange equations of this minimum problem, okay, they define a standard linear truss problem, okay? So here are the Euler-Lagrange equations for you. And this is one part of the one step in the iteration where we have identified for every member a possible material state from the material data set, okay, strain and a stress. And then you solve two standard linear truss problems to obtain the next admissible strain and the next admissible stress. Then, of course, you close the cycle by taking this strain and stress, going to the material data set and looking up again the nearest point in that set, and that would give you the starting point of the next iteration. But the big point here is that regardless of what the material data set is, okay, we have not made any statement about linearity or non-linearity of the data set. In fact, it's just a collection of points, okay? So linearity or non-linearity doesn't really apply to that situation. Regardless of what the material data set is, okay, the DD solver reduces to two standard linear problems, okay? So one standard linear problem with initial strains, one standard linear problem with initial stress. So one very important thing, I think, of model-free DD is that leads to solver standardization. So you divorce the solvers from the material data, so therefore you standardize the solvers. So all the boundary value problem aspects of the problem, the geometry of the domain, the loading, the boundary conditions, goes into these linear problems independently of the material behavior. And I think that's a big point also going for DD solvers, the fact that they lead to standardization. Okay, so that's very good for industry, that's very good for everyone. Okay? So these are just some examples. For instance, of course, very easy to put in inertia in the constraint set. Okay, that introduces a new field, which is the acceleration, but then you close the equations using Newmark, for instance. Okay? And here you have the truss jiggling, and at the same time, this is the material data set that we use in the calculations. These calculations are done without a material model, directly from this material data set, and you see here the coverage of the set as the solution evolves. And this is a comparison between the DD solution and the Newmark solution. You can see they're very close. Okay, from an engineering norm, they would be very close. Okay, so DD, of course, solves and gives you very reasonable solutions, okay, without a material model, just from a data set. We have extended these things to a number of situations, okay, where you have data, for instance, defined only in a probabilistic sense, noisy data, and so on. Also to inelasticity. In this case, of course, the data set, so you proceed incrementally in time, you're at some point here, epsilon k, sigma k in phase space. This is, of course, notional. And so the data set then would evolve in time, okay, because it's history dependent, and at any given time, we define all the possible states that are accessible from the current state of the material, okay? And so essentially what you have then, okay, is a sequence of time-dependent data sets that evolve in time, and they're conditioned to the history of the material, okay, however that history is defined. Okay, so therefore the material data set that you need is material history data. So for instance, from testing materials along selected loading paths, relevant loading paths, if you're interested in, for instance, proportional loading, you would just consider sufficient number of proportional, representative number of proportional loading paths, and of course the data, so the accuracy or the quality of the solution depends on providing sufficient coverage of the paths, the relevant paths for the problem, okay? So other than that, the data-driven problem is exactly the same thing. So you're minimizing a distance to a data set that evolves in time. So this time, the minimization is the same, but the data set is time-dependent, and also the constraint set, of course, can be time-dependent because the loads and the prescribed displacements can depend on time. So again, but the essential structure of the model-free DD problems carries over to the history-dependent case. So here are a couple of examples where we've done data-driven viscoelasticity. In this case, for instance, the simplest kind of conditioning to the history would be to make the material data set dependent on the initial conditions for the time step. That's enough, for instance, to approximate the standard linear solid. Okay, and so these calculations are finite element calculations. Okay, they're simple finite element calculations just to demonstrate the principle. Okay, so you have a beam here with the tip loading that is increased and then decreased, and the data is obtained, okay, it's synthetic data that is obtained from the standard linear solid, randomized. So we take the standard linear solid, we randomize it, and then we use those data as data for the data-driven problem. And you can see here how the tip displacement increases, then relaxes to 0, and this is the convergence towards the reference material model as the number of points in the material data set is increased. Okay, so you have convergence with respect to the data. Okay? And we've done also some data-driven plasticity calculations. This is courtesy of Robert Eggersman and Stephanie Reze from the Aachen team, or the A team for short. And in this particular case, the way they populated the data set was by solving a virtual test. And I'll come back to this in a second. So a virtual test that is designed to generate complex states of stress. So here we begin to see a philosophical departure from conventional experimental science. Okay, so traditional experimental science, testing, material testing, was designed so that the states of the material could be deduced easily. So typically, uniform deformations, uniform stresses, and so on. Okay. Now, if you want to populate a material data set, okay, with broad coverage, you want exactly the opposite. You want to design a test, in this case a virtual test, okay, with stress risers such as perforations or cracks that induce complex states of stress and deformation. Okay, so you get good coverage of phase space, and that's what Robert did with Stephanie. So ran this example. They assumed that you could actually measure both strains and stresses. Okay, that's a big assumption that can be relaxed, and I'll come to this in a second. And based on that material data set, they solved DD problem, and then they resolved the problem with the reference material model, and you can see that the solutions are very close. Okay, and again, you would get convergence, presumably, if you increase the number of points in the data set. And again, the data set calculations are model-free. They're done without a material model, okay? Just with the material data. Okay, so this is the overall picture of the flow of information in this kind of calculations, if you wish. You have a data warehouse that you have obtained somehow, and I'll devote the rest of the talk actually to discussing possible ways of populating your data warehouse. But you have your data warehouse, and differentiating aspect of it is that is fundamental data, okay? It's not data that is associated with or beholden to a particular model, okay? But it's fundamental data in phase space. Phase space being defined uniquely by the conservation laws. So at some point you have, okay, some boundary value problem that you want to solve. You have quadrature points. We know about quadrature points. And you want to populate, you want to match states in the data warehouse to the Gauss points. Of course, those states won't be compatible, won't be in equilibrium. Okay, so what you do then is you solve two standard linear problems, material independent, okay, to generate, based on that initial state, the admissible state that is closest to it in the L2 norm sense. So here, what you do is you're solving these two standard problems with the solver of your favorite solver, Abacus, Pheep, it doesn't matter. As long as you have access to the Gauss points, because you have to be able to populate the Gauss points and extract information from the Gauss points. That's the only requirement. So then you use your favorite solver here, and you generate now a new state that is admissible. So it's compatible and it's in equilibrium. Now, of course, that new state is not anywhere in the data house, in the warehouse. So you go back, so you extract now the data from the Gauss points, and you match it against your data warehouse, and you find the point in that data set that is closest to it, and you iterate until you converge. And when you converge, that's your data-driven solution. So that's a flow of information. And I would say, okay, so I've been in the business for some time. I think this is really a different way of doing things, okay, that has a number of advantages and perhaps some disadvantages. Okay, so material-free data-driven solvers, I would say, provide a new paradigm in computational mechanics that builds directly on material data and bypasses the material modeling step entirely. Okay, so that would be the advantage. DD solvers also have a number of other advantages. So from the standpoint of the solver, they lend themselves to standardization. So you're left just with solving a linear initial strain problem and a linear initial stress problem, regardless of the material behavior, regardless of whether you have linearized kinematics or finite kinematics. Okay, it's completely material independent. And then, okay, you, of course, then you have the problem of looking at things in big data files. And that, of course, requires some some doing, okay? So you have to use data structures, fast lookup algorithms, and so on, but that's standard computer science, okay? So that's been around for many, many years, okay? So that's the solver part of the business. Now, of course, the question is, where do you get the data from? And that's critical data, but it's also an important part of the ecosystem, okay? In a way, you'll see that everything fits together. It's not just the solvers. It's not just data mining. It's not just data repository. Everything kind of fits together in a happy way, okay, that provides a well-defined set of moving pieces that work together very nicely, okay? So now data mining, okay, where do we get the data from? And here we have basically two main ways of doing this. One is, again, going back to the fact that nowadays we have very powerful full-field microscopy methods, for instance, digital image correlation, or DIC, okay? And what those do is they provide full-field measurements of displacement and strain, okay? So from one single measurement, okay, you get a full field of strain, so you have a large number of strain states. Now, of course, you don't have the stresses, okay? So now what DD, another nice thing that DD does for you is that it sets forth kind of a self-consistent way of identifying the stresses experimentally, and then therefore leading to material sampling, okay? So the way that it's done is the following, and this is the contribution of the Nantes team, okay, Julien Retoré, Adrien Leig, and Laurent Stenier. So what they say is the following, okay, what have we been doing for the longest of times? We have been doing these kind of calculations for different applied loads and for different applied displacements. So alpha here would label the loading case. You have a number of loading cases. You can measure directly displacements and strains. Unfortunately, you cannot measure stresses. But we know a number of things about the stresses. Okay, it's not that we don't know anything about the stresses. We know that they have to be in equilibrium with the applied loads, and we know the applied loads. We know the geometry also of the specimen, and of course we know that the strains have to be compatible. Okay, so now DD provides a way of formulating a self-consistent loop that both identifies or solves this problem, okay, the boundary value problem that is used in the experiment, and identifies the stresses. And the way that is done now is to minimize, again, the L-true norm. These are the admissible sets, okay, epsilon and sigma, and now these are possible to be identified material states that are consistent with the constraints. So you can do this minimization, you can write all the Euler-Lagrange equations, you can solve them, okay, there are some conditions for existence and so on, but the whole thing goes through, and it works. Okay, so let me give you a couple of examples. So this is from, a virtual test, but done to, now, not assuming that you can measure the stresses, but actually to replicate the situation you would have in a typical DIC measurement. Okay, so you have now a specimen that is designed to have stress risers, and you have some loading paths. These are the displacement fields you would measure by microscopy. Now, you use the self-consistent DD material identification scheme that I showed earlier, and you have this coverage of this strain in the strain field and this coverage in the stress field. Of course, they are related by the material model that was used to solve the problem, okay? So that's kind of a sanity check to make sure that, okay, they reproduce the hidden underlying material model, which they do. So as you can see, you can sample the stresses, and the stresses are correct, okay? And so then this would be the corresponding, so now you take that data set and you use it to solve another problem. So in this case, it would be the problem of a plate with a perforation. And this is the solution, the stress field that is obtained from solving a finite element calculation with the original model, okay, unknown model, the hidden model, and this is the DD calculation that is done model-free. As you can see, they match quite closely. You can measure the error, of course, and establish that, in fact, you have convergence. Interestingly, okay, this is the coverage in strain space, okay, that you get in the model-free DD calculation. So this is the red is the entire data set, and green is the states of strain that are actually exercised or covered during the solution. As you can see, it's extremely non-uniform. So first of all, the phase field is of high dimensionality, so you cannot cover it uniformly. It has to be object-oriented if you want, okay. And okay, the self-consistent DD approach, however, provides you coverage of the area that is relevant to the problem, okay? So it's kind of important sampling, as opposed to uniform sampling that you could never do, okay? So, and here you have, some, as I was saying, you can measure the error in different ways, okay, and you can obtain convergence with respect to the number of points in the data set, okay? So the larger your sample is, the closer you are to the underlying problem, and that is shown here by these convergence plots. So that's one way, and the interesting thing is that this way of doing things cuts both ways, okay? It's not just interesting to generate material data sets for computing, but for generate or to suggest new experimental science paradigms, new types of experiments, okay? So experiments, as I said, with stress risers, okay, that give you in one go broad coverage of phase space. So for instance, again, the NAND group have used these perforated domains to obtain very large material data sets. These are actual material data obtained in the experiment, for instance, for stainless steel. And now my colleague, Ravichandran at Caltech, with his co-workers, is using these specimens, which they were using traditionally, but with perforations, again, to obtain a broad range of states of stress and strain. So data science is changing not just computing, but also experimental science. Okay, there is another way of obtaining data, which is from lower scale calculations. Okay, this I find very, very exciting. Okay, so here you have data-driven methods, okay, influencing multiscale modeling. Okay, so of course you can do, if you want to characterize a material, you can do molecular dynamics calculations. We have very powerful programs such as LAMMPS and so on, and these are some calculations that we did to characterize silica glass. So fused silica. Fused silica is actually plastic under pressure. Okay, so you can see here the data that we obtained. So for pressure volume, so this is just the specimen compressed. Okay, you compute the pressure and you unload and you get a whole bunch of data. Okay, and this would be the data that we obtained for pressure shear. Okay, so you test the material along relevant paths that you think you're going to need in your calculations. Of course, you can do that at temperature using standard thermostats, okay, both volumetric response and pressure shear. And you get data sets like this. Okay, the other nice thing you can do when you do MD calculations is that you can compute energy. Okay, so you can compute the free energy. So you can do a thermodynamic extension of data-driven where you add now two new conservation laws, the first and the second laws. Those are universal material-independent laws. They introduce thermodynamic variables like free energy that, okay, the equilibrium ones you can compute using molecular dynamics. Okay, so we do this once you have both stress, strain, and free energy. Of course, you can compute dissipation. And so we add that to the data set. And to make a long story short, we find these new variables useful in actually navigating these material data sets that have loading and unloading, okay, and determining loading and unloading conditions. Okay, so from the standpoint of data mining, okay, so DD, okay, so has a number of interesting properties. So for instance, can extract data from full field experimental microscopy. It can generate data from microscopy without prior assumptions about the material behavior. So you don't have to assume J2 plasticity, okay, and then compute the yield stress. You don't know anything about yield stress, okay? So you can identify fundamental data without any assumption about material behavior, okay? And of course, you can also mine data from lower scale calculations, and that defines a new multi-scale paradigm in a way. Okay, always the difficult part The difficult part of multiscale modeling was to upscale the data, okay, so to determine the effective behavior, if you want, at the upper scales. Okay, that was always part of the promise of multiscale modeling, but that promise was never realized, okay, except for some exceptional cases. So for the most part, multiscale modeling, okay, has been reduced to parameter passing. Okay, so you do calculations, not multiscale calculations, but calculations at multiple scales, okay? And then you use information from a lower scale to determine parameters of a model at the upper scale. Okay, now DD provides a different multiscale paradigm, which is that you just take the data from a lower scale and you use it in a model-free, data-driven calculation at an upper scale. Okay, so in a way, it fills the gap in multiscale modeling, which was always to determine the effective behavior, because now you don't need to determine any effective behavior. You use the data directly, okay? And I think DED sets forth a number of new opportunities for synergism between experimental science, scientific computing, and new multiscale data paradigms. Okay, I've run out of time, but I think one big opportunity here for industry is to set up data repositories that are fungible, because the fundamental data is totally fungible. It's like money, okay? You have a dollar bill from one source, a dollar bill from another source. You put them together, you don't care where they come from. Fundamental data is also fungible. So you can take different data sets from different provenances, put it together, okay? And I think that's a very, very powerful way of this type of data, leading perhaps to publicly editable repositories in the style of Wikipedia, okay? So imagine a repository where you can check in and check out data, okay, for free. And, okay, if anything goes well, that data repository would grow organically, okay? It would provide a new way for industry to generate and exchange data. Well, so I know this is going a bit fast. So it's a deep subject. So if you want to learn about all the gory details, maybe you would like to sign up for this system course that a number of us are offering next April. If you cannot go, send your students. Then your students will find out the details, and they will tell you all about it. And we'll look forward to seeing you in Udine next year. Okay, so this basically, as I see, the model-free data-driven ecosystem is a combination of things: solvers, data identification, multiscale analysis, data repositories. I think it's a field that is likely to grow for a number of reasons, which I said earlier. And it's in response to an increasingly data-rich world. This community has to come up with its place in this new data-rich world, and that's one of the reasons why I think the subject is here to stay. Thank you very much.